All right, welcome back. So we're going to do just some properties of the Laplace transform. Okay, this really goes with the last section as well. So the first property is this property that if, oh, sorry, I'm getting so used to writing in cursive. If L of f of s exists for s bigger than some alpha, okay, then the Laplace transform of e to the at f of s, I'm sorry, f of s, okay, exists for s bigger than alpha plus a. Okay, so we suppose that it exists for some s bigger than some alpha, then this thing's going to exist. Okay, it's pretty straightforward proof. Okay, you're just going to take L of e to the at f. I should write like of t, but I didn't do that earlier. And that's going to be the integral from 0 to infinity, okay, e to the negative st, e to the at, f of t, dt. Okay, we're just going to play around here with the exponents. So from 0 to infinity, and we're going to write e to the negative s minus a. Rewrite that, a little better, s minus at, f of t dt. Okay, and now, since the Laplace transform exists, okay, what does that mean? That means we know, since the Laplace transform exists, we know that this integral exists. Okay, so since that is true, okay, that means that this integral exists too. It just exists for a different set, right? So this means this exists for s minus a bigger than alpha, or s bigger than alpha plus a. Okay, so here in red, this is the fact that the Laplace transform exists. Okay, that's this whole statement. Okay, so in blue, what we have is that the Laplace transform of e to the at f of t of s exists. Okay, so just noting the difference between those two. Let me change the color here. Let me change that to orange. Okay. All right, the next thing to look at is the derivative. Again, this one's in the book, but it's such an important property, and the idea behind it is so powerful and so important that I want to talk about it as well. Okay, so Laplace transform of the derivative. Okay, so we're going to suppose that the Laplace transform of the function exists. I guess I should say, of course, we suppose. Okay. L of f of t, which is the integral from 0 to infinity, e to the negative st f of t dt, exists for s bigger than some alpha. Okay? Then, any sort of derivative that we can take, the Laplace transform exists. So let's start with just the derivative. Okay, so just starting with the derivative, we're going to take, that's going to be the integral from 0 to infinity, e to the negative st f prime of t dt. Okay, so now this is theoretically, we can do this by integration by parts. This is our dv. This is our u. Okay, so that means du is negative s e to the negative st, and v is f of t. Okay, so now let's take uv minus the integral of v du. Okay, so that's going to be uv is what? E to the negative st f of t from 0 to infinity. Okay, minus the integral from 0 to infinity v du. So that's going to be what? V du is, well, that's going to change to plus s e to the negative st f of t dt. Okay, now what happens here to this thing? Well, let's take the limit as t goes to infinity on the first part. Oops. So let's take the limit as t goes to infinity, e to the negative st times f of t from 0 to t. Okay, let me make this a little smaller, just so that I can fit this on the page. Okay, we're back. So, let's keep that part. Well, this part, you should see what it is. This part, I want you to notice. This is just the Laplace transform, right? So here we're going to get s times the Laplace transform of our f of t. Okay, this part we're still working on. So now here, what we're going to get, well, what happens as t goes to infinity? F of t decays faster than e to the negative st. The reason that we know that, okay, is because if the f didn't decay fast enough, then this Laplace transform wouldn't exist. Okay, so remember from last time, f has to be exponential order of order, some order less than s. Okay, so at t, this is going to become 0 at t, and you're just going to be left with hold on, I'm getting a negative sign somewhere. Nope, I was right. Negative f of 0, okay, because at 0, this is 1, okay, plus S L of f of s. Okay? All right, so I guess we'll go to a new video. I'll see you in the next video shortly.